Okay, in this example, we have a fixed support at x equals 0 and free end at x equals L. So we can see that we have a horizontal load P, and the beam will deflect like this with a delta, maximum deflection there. We can say that this deflection is the maximum deflection minus y of x. So in this example, we want to find the critical load. Find PCR. Okay. So we can first check the boundary conditions. We know that y at 0 is equal to 0. And the slope at 0 should also be equal to 0. Okay. And we know that y at L is equal to deflection delta. Okay. If we just draw a free body diagram, so we have goes like this, and we have a moment, and this P, and we have this P down here. This is just delta minus y. Okay, so if you take the sum, this is the positive, m at x equals 0. This should be equal to 0. And we have that m minus p times delta minus y equals 0. And that's m is then equal to minus p times delta minus y. Yeah, and this is obviously in the negative direction. Okay. We know that ei y double prime is equal to minus m. If we use that, we see that we have ei y double prime is then equal to the negative of this, which is just p times delta minus y. Okay. So we have ei y double prime is equal to p times delta minus p times y. So if we just collect all the y's on one side, we get ei y double prime plus py is equal to p delta. Now, as usual, we divide everything by ei and let k squared equal to p over ei. So we have y double prime plus k squared y is equal to k squared delta. Now we have a second order non-homogeneous differential equation where yh of x is equal to A cosine kx plus b sine kx. And yp of x, well, the right hand side there is just a constant term. So we can say that this is equal to k. Now if we take the first derivative of this particular solution, we get 0. Okay. Now if we take another derivative of this, obviously we get 0 as well. Now if we insert this into the governing equation, we get yp double prime plus k squared yp is equal to k squared t, or delta. We get 0 plus k squared times k. Yeah. This should be equal to k squared delta. So k is therefore equal to delta. So the general solution, y of x, is therefore equal to a cosine kx plus b sine kx plus k, which is delta. Okay, take the first derivative of this, we get minus a k sine kx plus bk cosine kx. And if we let use the boundary condition that y at 0 is equal to 0, we get that a must be equal to minus d, or delta. Okay. If we use the other boundary condition, y prime 0 equals 0, we get that bk is equal to 0. And here then b must be equal to 0. Okay, then we can update y of x. That is just minus delta cosine kx plus delta. So y of x, factor out a delta, we get delta times 1 minus cosine kx. I can look at the additional boundary condition that y at L is equal to delta. We see that we have delta times 1 minus cosine k L. This should be equal to delta. So we get that cancels. So we get 1 minus cosine k L is equal to 1. So minus cosine k L is equal to 0. In turn, let's take the arc cosine on both sides. We get that KL is equal to pi over 2 times 2n minus 1 for n equals 1, 2, 3, so on. Okay. Now, if we square both sides, we get that KL squared is equal to pi squared over 4. So we get k squared is equal to pi squared over 4 L squared. Use the fact that k squared is equal to p over e I. And we can solve for p. So Pn is actually equal to P is equal to pi squared EI over 4L squared. And that's the critical load. Yeah, so that was this example.